Hello, my name is Divyang, and this is going to be my presentation for exercise 5 for EE 104 in SJSU. Let me start by sharing my screen. Okay, so this is exercise 5. We're doing a curve fit with multivariables. This is going to be from lecture 3. So this first line, x0 is equal to x over 10 for x in range 100. It's basically making two variables by incrementing 0.1. And then as it increments by 0.1, the value is going to be determined by dividing by x. So in this case, for x in range 100. So we could change the range, but it would also have to match the second line of code, which is, in this case, x1 is equal to math.sine x over 10 for x in range 100. This will create a list of 100 values where each value is the sine of x over 10, and it generates a sinusoidal pattern. So this is not a cosine function, it's a sine function, so it's a sinusoidal, basically. Um, and so if we were to change the range, as I mentioned earlier, we would also have to change the range in line 18 as well. So line 16 and 18 have to match in range. Otherwise, there would be an error. So xa is equal to x0 comma x1. It's a tuple that will combine x0 and x1 into a single object. And xa is going to hold both the values of x0 and x1. So what we're doing is that we're saying, okay, whatever values you get in line 16 and whatever values you get for line 18, you want that assigned to variable xa. So that's what it's doing. And def rf x fx0 fx1, it's basically a function that takes three parameters and two arrays, and it's going to be scaled by the factors of x0 and x1. So that scaling will come from here. So we want this function to use the values of lines 16 and 18, and we want it to be scaled based on those values for x0 and x1. So it's like a function call. We're calling this function is basically utilizing the values that we have set here. So x0 is equal to x0 comma x1 is equal to x, and rv is equal to np dot sine np dot multiply x0 fx0 plus np dot sine np multiply x1 comma fx1. It's an element-wise multiplication of inputs in x0 and x1. So what we're saying is basically that the element-wise multiplication of each of these values, x0 and x1, we want it returned, and we want it to assign as variable rv. And then this line return rv is going to result is it's the result of a sine function that we've calculated here, and it's being stored back into rv. And within all this code, every value that gets returned to rv, that value will basically be the rf. So this is basically the entire function block. And yv is equal to rf x0 x1 2 comma 3. That's a function call. Yet again, that's going to be from the tuple xa and the scaling factors of fx0 and fx1. So this is basically a function call that's utilizing the values that we've calculated here, as well as here, the rf x fx0 fx1. It's basically another function call. So we're assigning all of this rf x0 x1 2 3 back into the variable yv. So this is a new variable that we've declared. And def nonlinear least squares. So this is a function that we're going to use to model the multiple variables and do a linear fit basically of the data into there. But because it's a sinusoidal, we're basically doing a nonlinear squares fitting. If this was like a straight line, or if it was a parabola, then we can maybe do a linear fit as shown in the earlier exercises. But in this case, we're going to do a nonlinear squares fitting. And that function is basically POPT, PCOV is equal to op.curve fit, RF, XA, YV, H0, H1. What we're doing is basically we're saying print POPT, so we're printing this entire line. And this line is basically, again, coming from here, this function declaration. So H0, H1 are going to be the two values that we use, which is being declared here when we assign it and we declare it under this function def nonlinear least squares. So once we do that, the PLT plot it's gonna show RF x0 comma x1 2 1 b minus, and then PLT plot RF x0 x1 POPTG. That's all showing the graph. That's for showing the graph in the console. So let me restart the console and let me run it again. So that's showing here. So as we can see, we're incrementing from 0, 20, 40, 60, 80, 100. That comes from this range, the x. And then all these values on the y-axis, that comes from here in the range. So the range of a list of 100 values. So that's from here, your y and your x-axis. So so when we have nonlinear least squares, 1, 1, we're basically saying, okay, the test one is going to use a hint function, and it's going to guess which values there are, and it's going to do a multiple variable fit across the sinusoidal. So we've got 1, 1, which is right here, 1, 1. We've got 1, 5. The 1, 1 is actually right here, this first graph that I've shown earlier. 1, 5 is going to be the second function. 2, 3, which is right here. So we're doing basically 5 test cases. And then finally here, this is the last one. Test 5 using the nonlinear squares function. So all of these functions are being called from here, or are being called from here, def nonlinear least squares. So this is basically a function call saying, hey, we want to use values 1, 5, and so the 1, 5 comes here. It's going to be a function to model the data using nonlinear squares fitting. So it's using a nonlinear squares fitting to making sure that it aligns with the sinusoidal function. That's basically what's happening. And then with test 2, it's the same thing. We're just choosing random values for 5 test cases. So it is right here. That's pretty much it for this code block. One thing is that all these import libraries, they're allowing us to make these graphs essentially. You have import matplotlib.pyplot. That's basically showing, okay, I want this MATLAB plot here. And then Skippy optimize, that's another built-in library within Python that we have to import in order to run the code. And then import math, we're again importing the math function because we're doing a sign operation. So in order to do a sign operation, you have to import the math library that's built in within Python. So that's for this exercise 5. Thank you for watching. Have a great day.